So let's wrap up the chapter again by looking at this equation we derived with various assumptions along the way, the boundary conditions, and starting with already idealized equations. This equation has to be valid for all positions in the meridional direction and all positions in the vertical direction. So the sums of the two terms in these brackets have to vanish. So finally, we assume that the dynamics are determined by processes inside the vertical range 1/4 of the atmospheric height less than z less than 3/4 of the atmospheric height. Hence, the approximation cosine 2 pi z over h equal to approximately equal to -1 is applicable. So you leave you take the YZ plane and you assume where the dynamics happen. So you can think of this as the cell, the meridional cell, basically extending from 1/4 of h to 3/4 of h. So anyway, we are making all sorts of assumptions. So you can think of these as very approximate solutions to idealized equations, which show some very interesting behavior, which have very good analogs in the real system as well. So we'll come back to that later on in terms of analogs. So the equations then become, by making some non-dimensionalization and not using new typically when you do that, you write the non-dimensional parameters or variables as x prime, y prime, z prime, and so on. So for simplicity, we just assume them to be again x, y, and z. And without going into what was done, I will just jump to the equations, which are the famous Lorenz equations that are always talked about in the context of chaos. So here dx dt is minus cx plus dy. So x depends on x itself and is coupled to y, and dy dt is coupled to x, z, and y, and z is coupled to, of course, x, y, and z as well. So this is what makes the system so nonlinear and allows for some very intricate behaviors which make the system chaotic, unpredictable, to have strange attractors, and so on and so forth. So this has 7 constants here, C, E, D, I don't know. You can see that they are complicated expressions, so it's not going to help much by looking at them, but you should just be aware that this is a very simple looking equation, but it has all these parameters here, C, D, E, F, G, H, and K, and the parameter choices determine the form of the solution, which is what we are introducing. So by introducing new dimensionless physical quantities t, x, y, and z in the following way, so that's what I said before. So you take the time with this complicated multiplier and still call it t, x call it x, y with this expression call it y, and z with this complicated expression call it z. But you can see the dependence of the time on atmospheric height and the time scale of the solution, if you wish, on the meridional extent in a quadratic way, and also the scale height of the atmosphere as 1 over h squared. I'm just calling it atmosphere, but this is our solution domain, and that's the x, that's the y, cubic dependence here, and quadratic dependence here. Again, cubic and quadratic dependences here. Actually, it's much more complicated when you take the full expression. So basically, that's what makes this system so nonlinear and depend on small changes in parameters leading to very different looking solutions, which can be oscillatory, jump from one regime to another, or a damped oscillation, and so on and so forth. So This brings us to this classical Lorenz-Saltzman model that looks like this. dx dt is minus sigma x plus sigma y. dy dt is minus xz plus rx minus y. dz dt is xy minus bz. Very simple looking equation with sigma, which is related to viscosity and the diffusivity, r, which is related to the temperature gradient in the horizontal, vertical, sorry, nu divided by nu k, cubic of the atmospheric domain, and the fifth order, so a squared divided by a to the fifth approximately, so that is cubic as well, and b is 4 over 1 plus a squared. It's easier to just look at the solutions. So here, first 3000 time steps of the time series yt, the structure function in the time of the Lorenz-Saltzman model with the classical parameter values r equal to 28, r is equal to 28, sigma is 10, sigma is, this ratio is 10, and b is 8 over 3, so 4 divided by 1 plus a squared is 8 over 3, and delta is 0.012 integrated using the Runge-Kutta scheme. Because this is non-linear, you obviously cannot solve it analytically, so you have to choose some numerical method. And remember, we said we never use Runge-Kutta in real climate models, but in this case the functional forms of the constants are known, hence we can use the Runge-Kutta method, and you can see that the solution in time looks like it is has negative and positive phases, and then there are abrupt transitions. So it's negative here for some time steps, then jumps to a positive value of yt, but this transition is very fast. It stays longer here and then comes back to negative, stays for a longer period, but also stays in the positive phase here with jumps from positive to negative and positive and so on. So there are regimes in the positive and negative values of yt, which seem to be longer in time scales, and there are transitions from one phase to the other, which are very rapid. As we said before, a dynamical system, basically it's deterministic in the sense we have functional forms at any given time and space, x and y and y, z and t, but the transition, the jump from one phase to the other seems very rapid, and they are quite unpredictable. That's what makes the system chaotic. So here is kind of interesting feature that you can see. Cross sections through the different planes in the x, y, z space. So these are not spatial coordinates now. Remember, x, y, z have been morphed into all kinds of complex constants of structures of the solutions of the Lorenz-Saltzman model. So these are XYZ space of the Lorenz-Saltzman model with classical parameter values that we mentioned here in the XZ plane. So you can see that they are not intersecting, they are just going in these loops around these let's say phase spaces, and these are what are called often the strange attractors. So the solutions seem to just go around these, and you can see here in the YZ plane, so this is YZ plane, so you can see that it has again not intersecting in the XZ or YZ plane or the XY plane, but transitioning from negative to positive values. Of course, Z is here all positive, and X can be positive and negative, Y can be positive and negative. So you can see these patterns which became very popular, and all kinds of amazing patterns were produced by playing with this equation and some other complex nonlinear dynamical systems equations, and that is the thing to remember, that they can stay here for a long time, but they transition quickly from this to this, so not much residence time in the at the jump between the phases, let's say. Okay, so as in 7.8, but you change the parameter to r equal to 20, sigma equal to 10, b equal to 8.3, 8 over 3, so that's kept the same. And now you can see that this looks like a damped oscillation, so it was positive, jumped around, then went negative, and then just kind of died away. Okay, and as in figure 7.8, but r equal to 100, sigma equal to 10, b equal to 8 over 3, and this one seems to kind of have transitions which are fast again, but staying in the positive longer here, and maybe also in the negative, but these transitions and back are very rapid. So that's what makes the transitions difficult to predict, and obviously I'm not really an expert on dynamical systems and chaos and so on, but I've just tried to explain the equations from the model, Lorenz Saltzman model from the book for continuity. There's enormous amount of literature on this, starting with Lorenz's classical papers from the 60s, and he did a lot of work on it for decades, including the Coriolis parameter in the 1980s. But it's much more fun to go and look at real coupled climate solutions and models and see in what conditions you may get chaotic behavior. But as we said before, this was most directly applicable to the weather prediction system, where, as we said before, if you look at the space where initialization is done, it can be a small circle, but as the solutions evolve, small errors grow into rapidly large deviations in the solution space. So this is what made the weather forecast system to be known as chaotic, but there are various ways in which now people look for predictability and it's very different in the mid-latitudes and in the tropics, because tropics have very fast convective systems. Mid-latitudes have basically large-scale synoptic systems that linger around for several days, so the predictability is predictability is high for several days, whereas in the tropics predictability tends to be very short. And then data assimilation and other methods are used to improve initial conditions, to reduce the errors in the initial conditions so that your solutions don't go chaotic very quickly. And while the weather forecast is possible only for a few days because of this chaotic phenomenon and dependence on initial value errors, we have to explain why climate can still have predictions at longer time scales, like seasons or multiple seasons. For example, El Nino, we said, can be predicted for 6 to 9 months. That's because, as we said before, the ocean that varies slowly controls the coupled system, and you get what is called predictability of the second kind. So coupled system has predictability at a longer time scale, but at shorter weather time scale, the atmosphere with its low heat capacity and low density can very quickly go chaotic. So that's exemplified by this system of simplified equations. And then there is lots and lots of papers and even books. Mandelbrot took this to another level, finding that there are fractals and so on in the biological systems, and so on and so forth. Fractals are basically, as we said before, systems that have self-similar patterns at all scales, and that relates to these dynamical systems and what we looked at here. But let me leave that here without adding any more confusion. Okay.